Welcome. In this tutorial, we'll establish techniques needed to lay out parallel lines. This is particularly important in the design context when you're trying to design casework. You might want the sides of a cabinet to be parallel, and so the techniques from this video will help you to do that. However, before we can get there, we need to establish one utility proposition of Euclid's, and that is the construction for how we copy an angle. And we'll state and demonstrate this construction without worrying about a proof this time. And so that proposition is proposition 23 of book 1. And it says, on a given straight line and at a point on it, to construct a rectilinear angle equal to a given rectilineal angle. So that's Euclid's proposition 23 from book 1 of the Elements. And here's what it means. You have some given rectilineal angle. And then you also have elsewhere in your geometric design some line segment with a point on that line segment, and you want to draw another line radiating out from that point so that the resulting angle equals this given angle. So let's label some things. Our given angle is going to be ABC. No, it's not. Where I drop stuff. Yeah. B is going to be our given line. CDE. There's our given angle. And so we want to construct an angle at point A on AB to match that. Here's how the process works. We are going to, on our given angle, mark the same distance on both legs. And I'm going to transfer that distance from point A onto line segment AB. But I'm going to do it where I swing a pretty good sized arc. So that, remember, this is the arc of a circle, so every point along that arc is the same distance away from point A. Now, I'm going to measure these two, I'm going to measure the distance between these two intersections on my original angle. Measure it, and then I'm going to transfer it over here. Put my tip of my compass on the line segment AB where that arc intersects it, And then with the marking tip, I'm going to draw an intersection elsewhere on the arc. That intersection, I'm going to connect point A to it with a new line segment. We'll label some of these other intersections that way. Now my claim is that this angle is going to be equal to that angle. So angle DCE equals HAB. In other words, I'm claiming that I've copied my original angle over to here. So why would that be true? Well, really the only technique that we've used with success so far was to establish that we had two congruent triangles and then demonstrate that the angles in question are corresponding angles to those triangles. We're going to do the same thing here. So here are the triangles. I'm going to show that triangle GCF has to be congruent to triangle AHB. But they've got to be, right? Because what I did is on my given angle, I marked out this distance CF and ensured that that was equal to the distance CG. But then I copied that distance over here to J, and swung this equidistant arc to AH, made sure that those sides were congruent. So this segment, this segment, this segment, and this segment, they're all equal to one another. And likewise, I measured this distance from F to G and copied that distance from J to H. So those sides have to be congruent. So what I really have here are two isosceles triangles that are congruent by side, side, side. This side corresponds to this side corresponds to this side corresponds to this side. So because of that, these two angles, which are corresponding angles in two congruent triangles by side, 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 they must be equal or congruent themselves. So angle DCE has to be equal to angle HAB. So that's how you can copy an angle. And we're going to use that in pretty much any of our techniques for laying out parallel lines. That's why we need this construction in this next video tutorial on parallel lines. Somehow I think I said I was going to state that without proof, and yet I went ahead and proved it anyway. I guess that's okay. It's good for the soul. But like we've seen with many of our constructions, it's not a bad idea to review them once. I don't know, both for the sake of additional practice and repetition, but also for seeing how you would quickly repeat these constructions in practice without making a whole bunch of additional marks. So just to go through the critical steps, if I want to copy this angle onto this line, all I've got to do is set my compass, point at the vertex of the angle, tip somewhere on one of the legs that's not so far apart that it will, it's still going to have to be able to intersect with both legs. I'll swing two arcs through there, and I'll swing one big arc through there. Set my compass to the distance between those first two intersections. transfer that distance over here. Once I've done that, I can connect this intersection to this endpoint. And I've copied my angle. So that's the efficient approach with kind of a minimal set of minimal set of additional marks that clutter up our diagram. So with that in place, we're really in a position to lay down some facts about parallel lines. Now remember, parallel lines, just as defined by Euclid, they're just any two lines drawn in the plane, straight lines drawn in the plane, that if you were to extend them infinitely in either direction, they never intersect. That's what a parallel line is. And we'd like to be able to draw lines that we know are going to be parallel. So Euclid states two propositions that are going to be critical for our way of constructing parallel lines. Now these I really will state without proof. So proposition 27 of book 1, it talks about, so I'm going to freehand sketch some parallel lines. I'll do the best I can to make them actually look parallel. Hope that's close. Doesn't look bad from this angle. And then I'm going to draw a third line that traverses them, that intersects both of them. So, proposition 27 of book 1 of the Elements says that if a straight line falling on two other straight lines makes the alternate interior angles equal, really just alternate angles in general, and in a minute I'll say what I mean by alternate angles. But these two that I've labeled here are alternate angles because they're on opposite sides of the traversal and on opposite lines in the network. But if those are equal, and those are the alternate interior ones, then these two lines are going to be parallel. And we indicate parallel lines with those arrow marks on the lines. So because these alternate interior angles are equal, these lines are parallel. That's what proposition 27 of book 1 says. Now, they don't have to be alternate interior angles that are equal. Those are alternate exterior angles. If you were able to demonstrate that those were equal, so they're alternate because they're on two different lines, and they are on opposite sides of the traversal. They're exterior because they're outside of the network of lines. So that's also sufficient. If you could show that those are equal, then you've got a parallel line network. So that's what proposition 27 says. Proposition 28 works with the same kind of network. And it says, look, if you've got a line that traverses two other lines, and if you can show, the wording stated carefully here, The opposite, so if you can show that these straight lines make the exterior angle equal to the interior and opposite angle on the same line. So here's an exterior angle. If you can show that it's equal to the interior and opposite angle on the same line, so this one's interior because it's in between the two lines. It's opposite because it is on the other of the two lines. It's not alternate, so it's on the same side of the traversal. Okay, so opposite interior versus exterior. If we can show that those are equal, then once again, we'll be able to conclude that those lines are parallel. So equal angles imply parallel lines. All right, so those are two propositions that actually require quite a bit of preliminary groundwork to be established in order for us to prove that they're true. And that's why we're just not taking the time to prove that they're true. These are often facts that are commonly just memorized in a high school geometry class. And I guess for our purposes of design, it's not too big of a crime to go ahead and follow suit and memorize them ourselves. But the proofs are available in the elements. You just have to work through several of the previous propositions before propositions 27 and 28 to really understand why these are true. But we're going to use them both in order to accomplish this task. Suppose you've got a line. And then you've got some point. So we've got our line. I don't know, I should label it probably. Might as well label it consistently with my own notes. You've got some point not on that line, and you want to draw a parallel line that passes through point A. It's parallel to this given line. That's your goal. Let's call this line BC, just so that it can have a name. All right, well, that is the subject of proposition 31 of book 1. It says so, Euclid's statement of that proposition is through a given point, this one, draw a straight line that's parallel to a given line. That's the goal that we stated a minute ago. So how would we do that? We've really got choices, but everything starts out the same way, at least at first. We're going to pick some arbitrary point D on our given line and draw a line that passes through our point A and that arbitrary point D. Label A, so it's a little bit more visible. We're going to do that. And so I want to be able to do something that's better than eyeballing. I want to be able to take my straight edge, put it on this point A, and reliably draw my line that passes through it so that it's parallel to this. Well, we've got these two propositions, 27 and 28, that tell us a couple of ways that we can maybe do that. If I could somehow ensure this angle for the line that I would have drawn up there equals this angle, alternate interior angles, then I would know that the lines are parallel. Well, I can force that to happen. All I've got to do is copy this angle to this line at this point, and I've got a construction that lets me do that. It's the construction we started this tutorial with. So I'm going to do that. I am going to set my compass to some arbitrary distance. mark 2 arcs here, turn my compass around. Oops, try not to move it. I'm going to start that over. Turn my compass around. Just going to get out of the way here. This is awkward. Swing a big arc like that. And I'm going to measure the distance from this intersection to this intersection. Going to transfer that distance from this intersection. Get out of the way of the camera. I'm going to transfer that distance from this intersection to somewhere else on this arc. And that intersection, that mark that I've made up there, is if I connect that to point A, then that new line should be parallel to this one. Because this angle and this angle, they're copies of each other and they are alternate interior angles. Right? So that's one way to construct a parallel set of lines. But I don't have to just work with the alternate interior angles. I could have copied, say, this angle up to here. An exterior angle copied from the opposite interior angle, its corresponding opposite interior angle. I could have done that. And that's certainly allowed. Let's verify that that works. And so what I'm doing is using either proposition 27 or 28 to figure out how to draw this line. So I'm going to use 28 now. I'll go ahead and copy that angle. Find my compass. So I'll make my 2 marks. Clean up this one that doesn't belong. And then I'm going to come up here to A. Swing a big arc. Then I'm going to find the distance between these 2 marks. Oh, back up. Need to make my picture a little bigger. Copied my arc in the wrong place. Extend this line just a little bit more. Mark where A is. And we'll back up and start over. So, what I said I had done is that I picked, trying not to stand in front of the camera and block the view, I picked this distance from D to the left, swung an arc up to here to match it. Now what I want to do swing an arc up here above A so that it's spanning an angle that's going to look like this. Now to copy that angle, I just measured the distance between this intersection and this one. Copy it from this intersection up here to where it passes through that arc. And that should give me a place where, if I did it at all accurately, and it looks like I had some error, pass through that intersection, we get 2 lines that are roughly parallel. So that's how you can construct 2 parallel lines. 2 different approaches. Either one of them is fine. Sometimes in a particular construction you might find that one works better than another, just depending on how much available space you've got. So not only is it going to be useful to be able to lay out parallels in our design work, we'll also see this parallel line construction again when we start subdividing a given line into an arbitrary number of equal segments. That's going to be our primary skill that we still need, in order to be able to start laying out rectangles that have sides that are in whole number rational relationships to each other.